let's take a look at the next section, 2.4, homogeneous differential equations. So for this, we're going to look at, oh, by the way, if we take a look at a problem or two that we've seen under, well, under any of these, but the separable differential equations, if you take a look at 3 and 4, on our way to separating them, you see that dy and dx are sitting by themselves. And actually, we've done differentials in Calc 1. I don't know if you've done it with your instructor, but differentials are covered in Calc 1. And so we're going to take advantage of the idea of differentials to take a look at differential equations, because you know, differential equations are essentially these differentials, and we're trying to find the original problem. So, for us to do that, we're going to take a look at this from a Calc 3 point of view. And if you've had Calc 3, then that's great. If you haven't, then don't worry about it. It's just a quick lesson on partial derivatives. So, if you have z is equal to f of xy, z is equal to some function, then you can find the differential of this the same way you, well, not exactly the same way, but more or less similar to how you found the differentials back in Calc 1, where you just take the derivative of the function and then you just tack on a dx to it. Except now, since we're dealing with two variables, x and y, we have to take the derivative of something with respect to x, and they call that, in Calc 3, they call it a partial derivative. And then you tack on a dx, and then you take the partial derivative with respect to y, and then tack on a dy. So in this first sentence over here, if z is equal to f of x, then the differential is going to be given by dz is equal to the partial of f, and that curly d is the notation for partial derivative with respect to x. And then multiply it with the dx, and notice the dx has a straight d. There's too many people squinting. And then we add on the partial derivative with respect to y, and then tack on a dy. So then you have your dx dy. So there's in the special case where f of xy is equal to a constant, how could that be a special case? Well, it's a special case. It's a special case. Anybody take Calc 3? What does it mean when f of xy is equal to a constant? Can you think about that, what that means graphically? Nah, it's okay. Let's not worry about it. What? A plane cuts it. You got the surface, and then you imagine the plane cutting it. What do you get? Anyways. Let's see, this is getting me excited now. So anyways, what we have here is that if f of xy is equal to a constant, then the derivative of z, the differential of z, is the derivative of the constant. And derivative of constant, as we all know, is equal to 0. So we have the differential here is going to end up equaling to 0. So let's take a little Calc 3 detour into things and come up with a function that we might see in Calc 3. So let's say f of xy is equal to, let's find a nice quadratic function maybe. So x squared minus 2 minus 3xy minus y squared, or y to the third, something like that. So suppose this is our function, and let's say this is a function in 3 dimensions. So imagine yourself in calculus 3, bring yourself back, whatever. So you get some sort of surface, whatever that surface might look like. Again, that doesn't matter. So let's find a differential of this. So what's the differential of this going to be? Imagine that this is equal to z. So just call it dz. So the differential is going to be some function times dx plus, whoa, what happened? Oh, the underlining thing. So dz is equal to some function times dx plus some function times dy. So let's actually, since we have the actual function that we can work with here, and again, this is just extra. What's the derivative of this function with respect to x? So the derivative with respect to x is pretending that y is a number. Just treat y as if it was a constant. So you just take the derivative with respect to x. So 2x minus 3y. Is that it? That's it. Okay, so that's easy enough. Pretending that y is a constant. Now, the dy is going to be the derivative of that function with respect to y, treating x as if it was a constant. So what's that going to be? Negative 3x minus 3y squared. So that's our differential dz. Okay? So now let's relate it to whatever it is we're doing. Oh, we're doing differential equations. So let's relate it to differential equations. What if this thing was actually equal to a constant? So let's go back to our graph. And this is how it would look like visualizing it. But now if we take a look at setting this equal to a constant, what is that going to look like? If we do this graphically and say this is equal to a constant, let's say 2, 3, 4, that picture doesn't really help much. Does it? Can you guys even see? Maybe if we zoom in or zoom out. So the interesting thing about this picture is that we're not interested in a 3-dimensional representation of this picture. We're interested in a 2-dimensional representation of this picture. So let's see if we can get to see a 2-dimensional representation of this picture. And what I'm going to do now is, well, it has something to do with that plane. Somebody mentioned the plane. It has something to do with the horizontal plane. Z is equal to 4, because that's what Z is supposed to be equal to. If you let Z is equal to 4. What's it called? Contour. Level curve, contour, diagram. So if we take a look at that on a different graph, and for me to change this into a different graph, I have to do some just special notation here. So this is a specific level curve where This is spinning too fast. If you imagine the surface, and then you find the intersection of the surface with the plane z is equal to 4, then this is the intersection that you would see. So now we're back in 2 dimensions. Now we can express this thing in 2 dimensions. If I were to graph x squared minus 3xy plus y cubed is equal to 4, this is the graph that I'm going to see. Okay, which this could be a possible solution to a differential equation, a first order ordinary differential equation. Okay? And then I really want to show you this because it's kind of cool. So you can make your cuts. As your cuts change, then your 2-dimensional contour curve is going to change. Pretty interesting, huh? Anyways, I can't wait to teach Calc 3 again. So back to our task at hand. In this special case where this is equal to a constant, this happens to be a solution to the differential equation this thing is equal to 0. So what we kind of did there is we kind of went backwards. Now, in our problems, we would normally be given these differential equations, and then we have to go backwards and find a solution. But I just wanted to show you where this idea comes from. Kind of like in the first order linear differential equations, we took an expression and we made it as if it was the answer to a product rule. And then we went backwards. So it's the same idea here. We're going to take this differential and say that this is an answer. This differential is an answer to a function. Then that would work. By the way, actually, it doesn't matter what this is, right? The 4, the c, because it's just a constant. So when we're finding the antiderivative, we're going to treat it like it's a constant. So that's our motivation for these types of, this is exact. These types of equations, this is called an exact equation. So let's define what it means to have an exact equation. So the definition here is a differential equation that's of this form, I should say is equal to 0. This is called an exact differential equation if it corresponds to some differential equation of some function f of x, y, defined in whatever region that we're talking about. So first order differential equation m times dx plus n times dy is equal to 0 said to be exact if the expression on the left-hand side is an exact differential equation. Oh, I guess this is an exact differential. Sorry. I was right. Maybe we should add dz equals that. All right. So that's the idea of an exact differential equation. Now, the other thing to do is try to figure out when we have an exact differential equation. So we have an exact differential equation. Kind kind of depends on if we know that there's a function that exists that this came from, where this differential equation, this differential, came from. And the way to do that is that, again, a Calc 3 theory says that there's something special about a function f of x, y when you take the differential of that. The first derivatives, actually, when you take the second derivatives of it, there's something that's happening there. So I'll try not to talk about Calc 3 so much anymore after this. But what we're going to want to do is when we see a differential equation like this, we want to be able to check to see if it's exact. Because if it is, then we're going to solve for it a certain way. So we need a criterion. And the way to check for this is that in Calculus 3, it turns out that if we take the derivative of the derivative with respect to x, if we take the derivative of this with respect to y, and then if we take the derivative of this with respect to x, then these two should be equal to each other. So that's called second order mixed partial derivatives. So what they're saying is that function next to the dx, right? You want to take the derivative of that function next to the dx with respect to y. And then you want to take the function that's next to the dy, take the derivative of that function next to the dy with respect to x. And if those two are equal, then you have an exact equation or an exact differential, and then you can say that that actually came from a function that you can find. All right? So this is going to be important to remember. You should remember this to check if something is an exact differential equation. Now, if you know that it's an exact differential equation, then you can try to recover the original function, f of x, y. So if we have we can find the original function z equals, or just say f of x, y, equaling to some constant, because we're assuming that, that thing's equal to 0. And so now that function is actually turned out to be an equation with just an x and a y. So that gives you a relationship between x and y, and it could give you an implicit solution. Okay, so what we'll do is we know the answer to this differential equation already, but let's see if we could take the same differential equation and go backwards. Okay, so let's take this differential equation. Let's see if we can go through the process of dealing with an exact differential equation and find the solution. So let's assume that this is our differential equation. And so whenever we see a differential equation, we want to identify the two functions that we're going to be dealing with, and we generally call it m and n. And so the m is that function next to the dx and the n is the function next to the dy. And make sure this is set equal to 0 so they're both on the same side. Otherwise, you'll be off by a negative sign or something. And then we want to figure out what m, the derivative of m with respect to y is equal to. So if you take the derivative of m with respect to y, what do you get? With respect to y? -3. And n, we want to take the derivative of n with respect to x. So that's also -3. So these two are equal, right? So we can say that this is exact. And then we move on. We'll try to solve for it. Now the solving for it part will rely on the fact that this is a differential of some function. And so this m is actually equal to the derivative of f with respect to x at some point, right? So we're interested in finding f, the f function. So to find the f function, what we want to do is we want to, well, the opposite of the derivative with respect to x, which is the integral. So we want to integrate m with respect to x, and we'll do integral with respect to x notation. So we want to find the integral of 2x minus 3y with respect to x, treating y as if it was a constant. So this is x squared minus 3xy plus c. Oh, we said we integrate treating y as if it was a constant, right? So this c might have a y in it. So I think they call it h and g or something. WRT is with respect to. So we have an expression h of y, which we initially put c because it was a constant. But since we're integrating with respect to x, y is a constant. So we really have a function of y, h of y, which is a constant with respect to x. Right? We know what the original problem was. So we're kind of moving towards that solution. And if you take a look at what we have so far, we only have two of the three pieces that we're looking for. Does that make sense so far? Now, this other n, this other function, was obtained by taking the derivative of the original function with respect to y. And so again, we're going to try to recover that original function by taking the integral with respect to y. And this is going to be minus 3xy minus y to the third power. Again, there's some constant with respect to the other variable that we're not using, so we'll call it g of x. Constant with respect to y. So this is a tricky part. I think the book, or maybe if you've taken Calc 3, you're going through the motions here, and you might have done things a little bit differently. But I like to do it this way because we lay it all out, and then at this point, what I want to do is I want to examine the things that they have in common whatever they have in common, you're just going to write one time. So I can see that there's a negative 3xy that they have in common. Okay, so that means the other piece that's not in common has to be a function of only x or a function of only y. Because that means that this x squared must be the g of x that we found in the second integral, and this negative y cubed must be the h of y that we saw in the first integral. Yeah. Say that again? Is the g of x is constant with respect to y. So instead of just saying it's constant, I might have some x's in there that I want to, and when I took the derivative with respect to y, all those x's disappeared. So now I can say that my function is going to be x squared minus 3xy minus y cubed. But again, remember that this is supposed to be equal to, it's not equal to f of x, it's not equal to z, it's actually equal to a constant. And that constant is some constant we don't know. So our actual solution is an implicit solution, x squared minus 3xy minus y cubed is equal to some constant. And we can make a note that this is an implicit solution. Try to solve for y, it's going to be kind of hard, so just leave it like that. Okay? It's supposed to be red. Any questions? Is this clear? Really? Half of you look confused. It's Fontaine. Exactly. Yeah, this is something that could have been covered in Calc 3. I think we're doing line integrals in Calc 3 or something like that and then trying to recover the function. Yeah. Then it probably wasn't exact to begin with. Because then if you have an x and a y, no, not always one in the middle. Here's what you would look for. If you have terms with both x's and y's, then that has to be common in both integrals. Okay, the terms that are not common in either integral would be terms that are only x's or only y's. Okay, that means they were constant and then disappeared in the process of differentiation. Any other questions? All right, let's see if we can find a problem. I don't think I picked out problems. I just say do these things. So let's, I don't know. Let's take out your book, I guess. Where's my book? All right. I got a lot to choose from here. Pick a number, 1 through 8. 7. 7 kind of looks similar to what we just did. 5 is similar. 8 looks interesting. 4 and 8. Let's try to do one of them. Let's start with 4 and then we'll take a look at doing number 8. Before we move on, we have to make sure that this is an exact differential equation. So let's double check to see if this is an exact differential equation. Let's first identify our functions as m and n. And remember, the check is the function next to the dx has to be taking the derivative with respect to the other variable y. So we want my and see if that's equal to the derivative of this with respect to y. Derivative sign is cosine. And here, y times x, don't use a product rule, right? It's just y. Sine x is a constant. What's the derivative of y? 1, so that's just a sine x. Okay. Now we want to take the derivative of the other function next to the dy, take the derivative of that with respect to x. What's the derivative of cosine? Negative sine x. And the derivative of x is, well, and then so we just have a cosine y. And the derivative of y, 0. Are they equal? So they are equal to each other, and so therefore they are exact. This is an exact differential equation. So we get to do what we are going to do now, which is integrate. So to try to recover your original function f, we're going to take the antiderivative of m with respect to x. So that's sine y minus y sine x dx. So this is with respect to x, so sine y is a constant. What's the integral of sine y with respect to x? Just x is just will pop up, right? And then sine y is constant. Just imagine taking the integral of 5. That's just 5x. And then the integral of sine x. Y is a constant. What's the integral of sine x? Negative cosine. So we have a negative and a negative. We'll make that into plus. Y is a constant. We have cosine x. And then we account for some possible constants as functions of y. I use g, h. I don't know. All right. Similarly, we're going to take the derivative of the n function, antiderivative, the integral of the n function with respect to y. So that's cosine x plus x cosine y minus y dy. And this is going to give us y cosine x plus derivative. The integral of cosine. Integral of cosine? Positive or negative? Positive x sine y minus 1/2 y squared. And then again, account for some constants. I think I switched my g and an h, but it doesn't matter. So we identify the things that they have in common. And we'll just write it down one time. So x sine y plus y cosine x. And then we have this extra term here that was missed in the first integral because y is a constant with respect to x. So that's a minus 1/2 y squared. So this is your f of xy function, but your solution is f of xy equal to a constant. So you just set this equal to a constant, and that's your solution. Again, you want to try to solve for y if you can. But if you can't, like in this case, you just say this is an implicit solution. What? We could say solution, but I would expect you to know that this is an implicit solution because y and x's are all kind of mixed up together. Any questions? Should we try another one, or are you guys getting bored? I know what. We can. Do they have any? Here's an initial value problem. Numbers 21 through 26. Oh, let's try number 24. That looks hard. Missing a parentheses, I think. So it looks like before we can even get started, we need to write it in the form that they are interested in seeing it in. And this is not in that form yet. So yeah, multiply by dt on both. Well, I think we need to take the other thing on the other side first, right? So let's do some algebra. Let's bring this over to the other side. So we're going to get a negative. And then I think I want to take the y to the 5th power and bring it over to the other side as well. So I will have, in a couple of steps, I will have 3y squared minus t squared dy is equal to negative t over 2y to the 4th, and then times 5, or y to the 5th dt. Oh, I have to bring it over to the other side anyways. Yeah. So cancel some stuff. What? The 4th? Okay, so we got one y left up on top, so that's just 1/2 yt dt. And let's bring that over to the other side. So this is 3y squared minus t squared dy is equal to, oops, plus 1/2 yt dt. So we'll do our usual checks. So there's x's and y's now became y's and t's. So let's be careful with that idea. This is some function. We can call it m with it next to the y. So we want the derivative of m to check if it's exact. So we're going to take the derivative of this thing with respect to the other variable t. So the partial with respect to t of 3y squared minus t squared. So the y is constant, so the first term is going to be 0. The derivative of this is negative 2t, right? And then we want the derivative of the second one with respect to y, 1/2 y t. So 1/2 t. Well, that's not exact. Oh, this section talks about the integrating factor. I don't want to do that. Yeah, you find an integrating factor. You want to do that? If I talk about it, it's going to have to go on a test. Because if they are not exactly exact, if they're close to being exact, like if you take those derivatives and it's just a function of one variable, like in our case, function of t, one of them is negative 2t and the other one's 1/2 t, so they're close, but not quite exact. To make them exact, you can multiply by integrating factor, and the integrating factor is e to the integral of my minus nx divided by m dx, or the other one. Want to do it? All right. Extra credit opportunity. Anybody who's interested can finish this problem using the integrating factor and videotape yourself explaining this problem. Okay? So I'd like to see this. I'd like to see you and this problem being done. So appropriate place to do it would be on a whiteboard or something. Yeah. Oh, no, no. This doesn't go on Epic. This is extra credit. You can, but I don't want this done. I don't want this particular problem done. There's an integrating factor in this section, and the integrating factor looks like this, which is different from the integrating factor for linear differential equations, right? Ooh, ooh. The picture of you guys taking a picture. Yeah. I want to see you in the videotape. So the other videotape, when you guys are doing this activity and stuff, you can just videotape yourself writing stuff down or whatever. But here for this extra credit, right? This is extra credit. You don't have to do it. I actually want to see your face as part of the presentation. I want to make sure it's you. Yeah. This is one extra credit point on the next test. 1 point. Well, that's what you think. Doesn't matter. This is one extra credit point. Take it or leave it. I mean, extra credit, so you don't have to do it. 1%, yeah, 1 point out of 100. All right. It's up to you. So I'll have a place for you to submit that if you want, and I'll make this a formal extra credit. Let's say this is due by Sunday, Thursday. No, not a week. So Sunday you guys have homework due. Let's make it due Saturday. It's extra credit. If you guys want to bitch about it, don't do it. Due Saturday. All right. So now we should still do one that actually doesn't involve. I wonder if I could do this in my head. This is 2x, 2y, 2x, 2y. All right, number 21 is. Well, let's see if there's one with an e to the x, e to the x, e to the y. 1. All right, number 22. Stop this one here. All right. We have room. So this is our problem. We want to know if this is, we want to find the differential equation solution for this. We want to check if this is exact. So we take, we'll call this m, the derivative of m with respect to y is going to be 1. And if we call this n, the derivative of n with respect to x is also equal to 1. So these two are equal. So this is exact. Which is good. Now we find our original function by taking the integral of m with respect to x. So that's the integral of e to the x plus y with respect to x. So e to the x plus xy plus some possible constant h of y, g, I don't know, whatever. It's a constant with respect to x. And then this same function, we should also be able to get by taking the derivative of n with respect to y, or the integral, sorry, the integral of n with respect to y. So that's 2 plus x plus y e to the y dy. So that's going to be 2y plus xy plus, oh, we have to do the, what's that called? Integration by parts. So do the integration by parts in your head, you're going to get y e to the y minus e to the y. Did you do it in your head? Is that what you got? Awesome. All right, move on. You guys know how to integrate by parts, right? Because you passed Calc 2 and you took the quiz and you reviewed the quiz. And so what do we have in common? So we know that this is for sure going to be, oh, that's not red. Of course, it's not red in your screen either. Oh. There it goes. So that's what we have in common. We have an e to the x. That's just the function of x, and then a couple of functions of y's here that we want to include as well. So your whole function f of xy is going to be xy is a function that we have in common. We have an e to the x. We have a 2y plus y e to the y minus e to the y is equal to a constant. Okay. Now we have an initial condition that says that y of 0 is equal to 1. So that's essentially saying that when x is equal to 0, y is equal to 1. So we want to put that into our equation. So we're going to put zeros in for the x's, ones in for the y's, and solve for the constant. So zeros in for the x's, ones in for the y's, and solve for c. So we got 0, this is a 1, this is a 2, this is an e minus e is equal to c. So c is equal to 3. So your solution, and what's this called again? It's an implicit solution, but the solution that we get after we solve for that constant using our initial condition. It's what? Specific, particular solution. So those other solutions with the C not solved for are called general solutions. So this is our particular solution. Got xy plus e to the x plus 2y plus y e to the y minus e to the y is equal to 3 is a particular solution. That means in the whole family of solutions that you might have been able to get, the one where this is equal to 3 is our specific solution. In fact, we can do that really quick with our graphing calculator. So we have x times y plus e to the y plus 2y plus y e to the y minus e to the y. Oh, I got one of the y's messed up. So for different values of c, the arbitrary constant, I will have different solutions. But in particular, we want the solution that passes through the point 0, 1. So the solution that passes through that point 0, 1 is c when c is equal to 3. So if you want to try to find a specific solution, c is equal to 3. And at some point over here, it stops becoming a function. So this will probably restrict your domain to go from wherever they start overlapping. And then you just look at a piece of the function. Okay. Any questions? All right. Let's look ahead to the next section, which is some sort of substitution. Now, the substitution in section 2.5 is not just one substitution method. It's actually 3 substitution methods that we're going to consider. So let's take a look at one of them. And one of them depends on this idea of what's called the homogeneous function and homogeneous differential equation. So we're moving on to section 2.5. For starters, one type of substitution that we're going to consider works for these differential equations called homogeneous differential equations. So a function f that has x and y in it has a property that if you replace x with t of x and you replace y with t of y and somehow be able to factor out a t to some power, then it's called a homogeneous function. Now, if you're taking linear algebra, or taken linear algebra before, and you've heard this word homogeneous relating to something equal to 0, unfortunately, this is not that type of definition. And the word homogeneous in this case is is not the mathematical term for homogeneous that you might have seen. In fact, we're going to use homogeneous in this class in a different way, similar to what we use in linear algebra, and it's not this. Anyways, this is a homogeneous function if it has this property. First order differential equation of the same form that we've been looking at, is called homogeneous if both the functions next to the dx and next to the dy are both homogeneous functions of the same degree. And to solve for this, we're going to use a special substitution. So that's the background work for that, and it doesn't make much sense to continue talking about the theory behind this. And actually, you can if you want to, but we're gonna dig in and do examples, and hopefully, it'll clear up what that means. So let's do an example. Looks like I have some examples picked out over here. Let's do number 5. So we have to show that it's homogeneous of the same order, and the way to do that is to check each of the functions by putting in t times x and t times y. So wherever I see an x, I'm going to put tx, and whenever I see a y, I'm going to put ty. So I have in for y, ty, in for y, I have ty, and then in for x, I have tx. All right, so this is my y squared plus y times x business. Now, algebra tells me that I'm going to get t squared y squared plus, I got t's and t's, so that's t squared yx. So I can factor out a ty, or a t squared, y squared plus yx. So it's homogeneous where alpha is equal to 2, at least for the first one. Now, if I do that for the second one, and I'm going to get t to the second power again, then I can say they're homogeneous of the same order, and then I can move on with that substitution. So let's check that. And that happens to be fairly easy. Because it's just a negative x squared. So in for x, I'm going to replace it with a tx. And that's going to give me a negative t squared x squared. Or more precisely, if I take it out, so to speak, I can clearly see that this is t squared times my original function, n. So I have the same power, so this homogeneous of the same same degree, yeah, homogeneous of the same degree. So, okay, then I can use a substitution. So now it comes time where we're going to actually try to solve for this. Let's use a substitution. Let's use, I don't know. Let's use the first one and see what happens. Y is equal to u times x. So what I'm essentially doing is I'm going to replace all the y's with u's and x's. And so all the y's will disappear. And what that means is that I'm going to have a new differential equation with an x and a u and no more y's. So what does that mean? I'm going to replace this with a u times x squared u times x dx. So I'm replacing all the y's with u times x's. Minus x squared times, dy. Looks like I need to find a differential of this, right? So dy is equal to, now this has two variables. Remember, the differential is something that has two variables. You take the derivative with respect to one variable times d of that same variable, and then you take the derivative with respect to the other variable and then times d of that variable. So the derivative of this, we have to assume now that it's they're both, what do you call it? Oh, you know what? Instead of doing it that way, sorry, that'll probably come out to be the same. But instead of doing it that way, let's think about it as a product rule. So it's the first times the derivative of the second plus the second times the derivative of the first. I mean, you get the same result, right? But I think thinking about it as a product rule would be easier. So this is dy. So now I have x's and u's in my differential equation. I suppose I can try to simplify this a little bit. This would be u x squared dx minus x cubed du, and this is a dx thing. U x squared dx plus u x squared dx. And so if I can combine, oh, look at these two, they cancel, and then that's nice, right? And then I have ux squared dx minus 3, or x cubed du is equal to 0. What do we do now? Any ideas? Oh, we could check if it's an exact differential equation, right? Wait, what did we learn before that? What was the first algebraic symbolic method we learned? Do you remember what it's called? 2.2. Separable. Is this a separable differential equation? Remember that a separable differential equation is the easiest differential equation to do. It's just like a u substitution. When you're doing an integral, the easiest technique is a regular u substitution. So whenever we're taking integrals, we want to always check if we can do a u substitution. Whenever we're doing a differential equation, the first thing you should look for is ask yourself, is it separable? This is for a first order. Is it a separable differential equation? If it is, then we can work it out easily. If it's not, then we have to go through a few more different things. Is it separable? It is. So this is u squared x squared dx. We can start to separate it is equal to x cubed du. And let's put the dx's on one side. What's the dx? What's a dx side going to have? What? Dx divided by x. And what's the u going to have? Du divided by u squared. All right. So now it's easier to do. So this is an ln x. We'll do the plus c's later. I suppose we should do the plus c's now. And this is ln of u squared? No. Negative 1 over u. U to the negative 2 power. Oh, there's a 2 that comes out, right? Negative 2 u to the negative first power. Oops, I got one too many negatives, I suppose. Is that good? So is that it? Do we have our general solution? If we integrate? And then we add 1 is negative 1? Okay. So we good? Is this our answer? If we could try to make it explicit, what are we solving for? Y? Oh, there's no y here. We have to put the y's back. Oh. What's y equal to? Or I guess I should say, what does u equal to? So y is equal to u times x, so u is equal to y over x. And then, so this is ln x plus c is equal to negative x over y. I suppose it's easy enough to solve, right? You do the reciprocal and solve. Y is equal to, let's see, reciprocal and bring the y, x. Is that right? Oh, yeah. I keep forgetting my negatives. So this is negative, that's negative. Is that good? All right. And if we had an initial condition, we put that in there. Technically, we should have an absolute value on the x's when we take the ln. So in case the initial condition might have a negative x value, then we just want to compensate for that. Right? Any questions? All right. So your epic, maybe you guys can work on, make sure you do the videos for the actual separable and first order linear differential equations. And she's not going to talk about the extra credit because that's for you to do. All right. See you guys next time.